All right, so if you would log into Canvas, and then at the top it has like the admin tab, and then it has the bonded module. It may already be open up, I don't know, but click on it, and at the bottom, you'll see a header that says practice quizzes, and below that, you will see bonded reactivity trends, hot and cold. Oh, maybe that's hidden, I noticed. Can you guys see that? Okay, this part wasn't actually there. It's kind of dumb, you have to publish the header, but whatever. Okay, please use your periodic tables that we used yesterday. You left it at home. Well, that was silly. You should bring it every time. All right, so let's take about 5 minutes and see how we do on that assessment. Okay, so 89% is our overall score on this for this hour. That's pretty good. I have literally no problem with that. We have one person that failed. Maybe they didn't have their periodic table, or maybe they just selected answers and paid no attention. So these are remember, you wouldn't fill it out on your periodic table yesterday and you said you were just going to memorize it. Who remembers that moment? Everybody does. So that's weird. That might be why it was hard. The rest of us have arrows on our periodic table that tell us how things react. So that's kind of how we're going to do it. All right, so just scrolling through here, doing pretty good. We got down here, fluorine. Oh, that's probably why. You don't know the symbol for iodine, maybe. So I should change that to an I, and maybe our score will go up. F is higher on the periodic table than fluorine. I think I have it right here. This is a better one I made a few years ago. Since F is here, iodine is here, the arrow points up, fluorine would be more reactive. I went in this morning and thought I changed them all the symbols, and I did that, but I forgot that one, but we'll be all right. 7 and 1. I feel pretty good. Ooh, that one didn't go so well. Which is more reactive, PB or OS? PB is right here. OS is probably not on this chart. Where is it? So it's probably in here. That would probably be why that one was a little bit lower score. I'll take that one off the test. I apologize about that one. But it would be less, or OS would be higher. I don't remember how the thing was written. Which is more reactive. Yep, the one lefter is. So, I mean, still not that bad. 80%, pretty good. All right, are we comfortable with this? All right, on the test, this is actually 2 different quizzes. So it seems crazy, but that right there is worth 16% of your test score. It's really not that bad. So don't tell people this class is hard. Just tell people that you suck at this class. Just kidding. You would never do that. All right, so hopefully you feel all right. Hopefully you have these labeled. We have these arrows. I don't have those written down here. And then we should be really pretty much good to go. Okay, so today we have just a little bit of the bottom of page 3 to wrap up. Does that sound right? Okay, let's see if I even have it anywhere on here. I don't think I do. Okay, let me cut it and then just drop it in here and we'll go over it. You know what? Can't make up my mind. I think I showed you yesterday, but anytime if you are home during like quarantine or anything and we start a new lab book, you can always find the PDF for the lab book at the top. So I'll just use that when I go to scan here. So this bottom part. Right here. All right, part B will help us answer a few more homework problems. Ooh, you do not need glasses. That is a little bit fuzzy. All right, so this, I used to do this in a lab, but it just was too messy and too many kids would chemically burn their fingertips. So we just do it now on paper. So just fill this in. This would have been like blue, whatever, green, red. All right, so what we would have done in this lab is you take little tiny pieces of paper, you dip them in these solutions and they change color. And based on those colors, hey, good job, Odessa, passed your food and nutrition. That is $30 to your local school. Congratulations, and thank you. Okay, so these papers are called pH papers. You dip them in, they change color, and you compare them to a chart that's numbered, and the numbers correspond to the colors. So blue is about a 12, green is a 7, red is a 2. So 12, 12, 7, 7, 2, 2. Now, those numbers are corresponding to how acidic the substance is, or basic, whichever way you want to describe it. And so what we would learn in this lab is the oxides. And if you'll all just look, Na oxide, Mg oxide, Al oxide, all of these things are when we're bonding them with an oxygen. So like this would be Na2O, MgO, Al2O3. All right, SiO2, P2O5, and SO2. That would be the formula of those things. All of them are the oxide. So whenever we say a metallic oxide, we mean when a metal is bonded to an oxygen. Okay, so if we look at this data table, it says the oxides of metals are blank, and that means pH values 8 to 14. So we know they are basic. So if I have a solution that has a metallic oxide in it, the pH of that solution is a high number, which means it's basic. Okay, then the oxides of nonmetals, they are the low numbers, so they are acidic. So anything under a 7 is an acid. Then the oxides of elements around the metal staircase have neutral pHs. All right. This corresponds to a little section of homework we'll do in a minute, but let's look at questions 1, 2, and 3 real quick. So these two apply to the lab we did yesterday. This one applies to the stuff filled in right here. So up above in part A on yours, which elements belong to family 7? They were fluorine. Someone help me out here. Chlorine, bromine, iodine. That one is in there, but we didn't test it. So you can write that. It's called astatine or just AT. Okay, then from the arrows, you can do this one on your own. Rank family 7 elements from highest reactivity to lowest reactivity. Oh, spoiler alert. It's already on the screen somewhere. All right, tell your partner which one's the most reactive one. Nice, birthday boy. Yep. Big 17 today. Yeah, 17 was my favorite year. Oh man, I had a lot of fun when I was 17. Or more technically, my junior year of high school, but whatever. Okay, so really the answer to number 2 is the same as I just wrote right here. They're the same. Okay, then number 3, how does pH change across the periodic table? I've taken this off of a test, but I've never taken it off the lab book. Just know pH decreases when we go left, sorry, we go right, oh my heavens, to left. You don't need to put an arrow on that, just answer that question, but you don't need to add anything to your periodic table because I don't test it anymore. Okay, so now what I need you guys to do is to turn to page 15, and I will keep this up here because to answer those questions on page 15, you need this section right here. I will keep it up, but you look at page 15, and it's problems number 21 through 26. So question number 21, Amber, the oxide of what? What's the first one? Is it BaO? Yeah. All right. So it wants to know if BaO is an acid, base, or neutral. So what we need to do is just find Ba on our periodic table, and Ba is right here. So is that a metal, non-metal, or metalloid? It's a metal. So according to that thing we just did, the oxide of a metal is a base. Page 15, number 21. Okay, so for each one of them, just look at the first element, determine if it's a metal, non-metal, or metalloid. And then you have that right there. If it's a metal, it's a base. If it's a non-metal, it's an acid. If it's on the staircase, it's neutral. Okay. I mean, any of these. Oh, that was the best sideways circling of my life. The ones touching it. Okay, do it on your own for a minute, then compare your answers to your lab partner. I'll come back here. Let me erase it so it's more clear. Oh, that made it worse. All right. Yes. Yes. I was explaining how the atom is mostly nothing. We are made out of atoms. So thus, we are basically nothing. Never will be, never have been.
Where are you looking? Oh, that's his bipolar.
Right above it is a blue hand, and right above that is a picture that says, so basically, you are nothing. One year I tried to start a career as a demotivational speaker, but they told me I wouldn't be good at it. That's a joke. I thought it was funny. I don't know. Thank you, Orvierdin, for your charity there. How's Instagram?
Great.
Good. Oh, man, that's awesome. Okay, check with your partner. Make sure you guys match on those 6. See if you are done with 1 through 26 now. And we're like, I don't know, 20%.
Wait.
Odessa, you good?
Hold on, I got a question. So,
Aluminum is a metal, but it's on the staircase, so we'd say neutral. Yeah, I'd say it's neutral.
Okay. Now we're the same.
Now you're the same. Okay. So we're just a few days in. We've gotten 2 parts of the exam ready. The test is still forever away, so don't panic. We'll be good to go. So now, if you would, turn to page 4, and it's finally a day where we're going to do notes, which I know everyone loves note day. Thanks, Kira. I had a girl come up after 5th hour yesterday. She's like, not to be mean, Davidson, but you're super boring. Well, that made my day. I mean, we did a lab. We talked about it. I did everything I could, and no offense, I'm boring. Well, I said to her, no offense, you're ugly. And then we just moved on from there. I said no offense, so it couldn't have hurt her feelings, right? All right, so we have, I think, sorry, at the top, oh crap, sorry, David. At the top, there's some questions which I don't think I ever cut in, so maybe, oh, Tom. They're nowhere. Okay, so let's just go back here. I'll read them from this. At the top of page 4 says, draw a line. These are the arrowheads for reactivity. So we did that part. All right, we've got that done. And then, right, reacts with cold water and acid, hot water and acid. Like I did a little bit different this year, but we did that. And we just rocked a quiz on that. Okay, so there are 4 conclusion questions. Let's answer them together pretty quickly. So what does the heavy stair-step line on the table separate? Tell your partner for 10 seconds. What is the staircase separating? Ready, go. 9, 8, 7, 6, 5. Metals and non-metals. We didn't even need 10 seconds for that. All right. You might need 10 seconds to write it. So page 4, right here, metals and non-metals. All right, 10 seconds with your partner. Number 2, why shouldn't the reactivity lines include family 8? All right, wow, that was more like you told the whole class. Well, it's your birthday, you wanted to share. That's true, you don't have a close lab partner. Does anyone sit there normally? Oh, okay, all right, yeah. Okay, so they're noble gases. Noble gases do not react. We'll learn about why today, actually. All right, based on our results, would Mg or Na react more vigorously in cold water? Na, because it's lefter, correct? Na. Now, don't call me out on this next question. It was poorly written, but just get over it. How about Be or Mg? Which one, if they reacted in cold water, which one would? Mg. Mg. It was bad writing on Mr. Davidson's part. Oh, I didn't realize how close this desk is. Oh, sorry, we good now? I don't want to spread the germs. Okay. Next. Wow. Wow. You are just on fire today. Fluorine is the most reactive. So I have a question. See if you can figure this out. What 2 elements would form the strongest bond when they are together? How do you know that, genius?
Because they're the most reactive.
All right, good. Okay, whoops, that's the wrong button. That's what I need. Okay, so that was perfect. We have francium fluoride. Both of these are extremely reactive, and they give off tons of energy when they react. All right, the energy they gave off would be equal to, but opposite direction, the energy required to break them up. So if we could ever get francium fluoride to form a bond, that would be the strongest bonded substance that we'd have. Well, binary. Binary means of just 2 elements stuck together. All right, and that's because of their reactivity. Okay, so now we have those summary questions rock solid. I think we are here. Sound about right? I wasted some of my Thanksgiving weekend watching a 10-hour documentary about Florida football because I don't know. I mean, I'm old and I watch documentaries, and like they say her. Anytime they go to say the word here, it's like her. So you see how we got Valence Electrons. It was so hard to understand them. Oh man. Oh, sorry. I've warned you. I swear I have ADD. I went to get checked, but I forgot to show up. Okay. Valence electrons. Raise your hands if you've heard of the term valence electrons before. Everyone has. That's not. I mean, everyone that isn't raising their hand has not. That's a lot of people. All right. Well, let's visit. Valence electrons are the electrons in the highest occupied energy level of an atom. Okay, so I have this erased. Let's just redraw it by hitting unerase. When we talk about valence electrons, when we talk about the highest occupied energy level, we mean everything in the level with this big number. So we had one, it was full. Then we went to the second row of the periodic table, and we mean everything there. So this atom, which is atom 1, 2, 3, 4, 5, 6, sorry, I almost counted 7. So 6, this is carbon. Carbon would have 1, 2, 3, 4 valence electrons. We all right with that? Carbon has 4 valence electrons. They're the ones in the highest level of the diagrams we would draw. All right, now the level is determined by the number, not the letter. Okay. Now, electron dot structures show valence electrons as dots. Now, Cullimore, Goddard, and I teach these all in a different way. It does not matter how you draw their dots. It just matters that you draw the right number of dots. So if we look at aluminum, aluminum is in family 3, which means it has 3 dots. I put 2 on the right, and then I go counterclockwise 1 at a time. That's a beautiful structure right there. You'll see what I mean. All right, but when we've been drawing the dots, we've been drawing the valence electrons. Now, does anyone remember how we determined the number of dots? It was a pretty simple process. Who remembers? How? It's the family number. Fantastic job, Kennedy. It's the family number. So if the dots are equal to valence numbers, or sorry, valence electrons, and dots are equal to family number, then family number must tell you the number of valence electrons. It's like A equals B, B equals C, so A must equal C. I don't know what property that is. I failed math. Just kidding. I got an A in math once. Okay, I'll be about. You what? Oh, hey. So here we go. If I had aluminum, 3 dots. Tell your partner, how many dots would magnesium have then? Oh, no. That didn't work very well. 2 is correct because it's in family 2. I'd put them there. If you put them on top, great. Left, great. Bottom, great. If you put 1 here and there, I wouldn't even mark it wrong. As long as you had 2, we'd be golden. Okay, dots, valence electrons, family number, all the same. Okay, so electrons are shown as dots in the following diagram. So 1, 2, 3, 4, 5, 6, 7, 8, whatever. Just put those 8 dots around it. I really don't care where they go. I used to, but I really don't care anymore. Through counseling, I work through my issues. All right, so neon. When we would have done this chart, it would have had 10 total electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But it only has 8 valence electrons because the bottom here is considered what we call a core electron. A core electron is a non-valence electron. I don't know. That's stupid that I laughed, but just trust me. That was a funny statement. Okay. This is good stuff here. Valence electrons are the only electrons used in formation of bonds. So they determine the chemical properties of an element. This is super important. On your exam, there's a section called bonded concepts, and most of those multiple choice questions come from the notes that we're doing today. So one of them is basically this, just not as a definition. Look how bad A. Goddard looks over there with his umbrella corp thing and his welding safety glasses and his mask. That man is a bad A right there. You look that up in the dictionary. I got to grow my hair out. It's official. All right. So here we go. So the question I often ask is, so why do the elements in the same family have the same chemical properties? What? Careful. Add one more word to that. They have the same number of valence electrons. Everything in family 1, hey, that's not going to work. That's white ink. Everything in family 1 has 1 valence electron. Everything in family 2 has 2 valence electrons. Everything in family 3, this is getting old, but you kind of get the idea. They have the same number of valence electrons. And so what we just read in the notes is the valence electrons are the ones used in chemical bonds, so they determine the chemical properties of an element. All right, so please make sure valence electrons determine the chemical properties, and that is why elements in the same family have the same chemical properties. All right. Oh, well, this is cute. So when we did this the first day, I put sodium in water and it fizzed. Do you remember that? That like sizzle sound was when the hydrogen was produced, and the water went pink because I produced a hydroxide. When I put potassium in water, the reaction is exactly the same, except for I just have a K instead of an NaO, or sorry, instead of an Na. It went pink, it sizzled, and then it lit on fire because this one's really hot, but it produced hydrogen gas. Rubidium, water, same products. Cesium with water, same products. Francium with water, same products. They all behave the same because all of them had 1 valence electron that they will lose in a chemical reaction. Yes. The first slide. Dots. All right. So same family, same properties. Okay, so here we go. What is the electron dot representation of Si? It's an Si with 4 dots. I used to joke that it was a S and a line with 5 dots, but that's not funny. See, it's not funny. Technically, Si has 5 dots because you got to dot the I first. Tell me that's not just true chemistry, English humor when your 2 least favorite classes combine, language arts and chemistry. Oh man, imagine that, baby. All right, give the electron configuration for the valence electrons of Si. Usually I make you write them out, but I already have them written gigantic right there. So the valence electrons configuration is just the last part with the highest number. So we look here, we have a 1, we have 2s, we have 3s. The 3s are my highest numbers, so those represent my valence electrons. Another way to know that we're right is Si is in family 4. This blue marker is just not showing up very well. Let's go light gray. It's in family 4. So how many total valence electrons should it have? It should have 4. 2 plus 2 equals 4. Like there's all sorts of different ways that the periodic table proves itself to be true. It's pretty awesome. All right, so here's this. It's a VI with 7 dots, and then this is a S with a 2, a P with a 5, and blanks. Now, you don't ever have to do this just on a test. But if we talk just valence, you go to the end, you look at what's there, and you account for those. Okay, now this is a good time to do something that I definitely skipped on accident. I wonder if I even have it here. I swear I do. Don't look. You'll get, oh, maybe. Dang it. Just trust me. Oh, maybe right there. Nope. You suck at teaching, Tom Davidson. Okay, I'm going to come right here. There we go. Nope, I'm looking for this thing. All right, my good friends. Oh. Last trimester, I neglected to fill in these two. How many people have those already filled in? Just one? Oh my, what's the top one say?
I remember.
Here, hand me that. Okay, so I forgot to do these. The top one is the generalized electron configuration for the family. So right here, you will just put an N. An N represents the row, and then it's S1, N, S2. So right at the bottom, do you have yours, David? You guys all know where I'm talking? The bottom of this one? Of the half one that looks like the one on the screen? Okay, now it gets a little, you got to write really small. This one was NS2 NP1, NS2 NP2, and you just keep repeating. You're adding 1 to the P each time until you get to this box. So NS2 NP3, NS2 NP4. That looks like a U, but I promise it's an N. Okay, fill those in. Though that part is not.
Yeah.
Okay,
Yes.
we'll put something
We gotta
else
fill
there.
that one out.
Okay, we will after we do page 14 here. It's all right. Take that periodic table and flip it over. Don't open it, just flip it over. And you'll see at the bottom those rows. Okay. Then, if you already did this, it'll be a little bit different than I do it, but it doesn't matter. Just leave it the way you have it. You put an X and 1 dot, and then an X and 2 dots, X and 3 dots. Like kind of, but not really. Okay, so each time you go over, you add 1 more dot. Just make sure you never have more than 2 dots on one side. Okay, now let me get rid of this. That was the wrong button. It's supposed to be that button. I do that a lot, actually. Let's see, I think it is. Nope, it wasn't that button. I swear it was that button, but oh well. that was weird how that thinned that up, but we'll live. Okay. So when we got to that little sliver of notes of just a second ago, and it said draw the general configuration and dots for the family, you could have looked right down here on your periodic table. What the N is equal to the row number. So now this is actually tested last try. So, I mean, it is helpful now, but it's not on a test. So what we would say is like, if we wanted the valence for Ca, we could look right here. And then we'd say, all right, it's NS2. Ca is in the fourth row, so it would be 4S2. That's how this is helpful. And then we'd also know Ca is represented by the X, and it just has 2 dots. All right, that's how we use that. Okay, let's go back way over here. All right, so the octet rule, about where we are, correct? The top of page 5. Man, the octet rule governs pretty much everything we do. Here's a good joke. Oh, man. Tanner loved it. Okay, so the atom says, I just lost an electron. Then the other one says, are you sure? Yes, I'm positive. Okay. Oh, man, I'll be here all week. Let your friends know. All right. Okay, here we go. Atoms react by changing. There are 3 ways an atom can change its valence electrons. It can lose when an atom, and I would add the things I write on here. When an atom loses an electron, we have a name for that. We call it a metal. And I've said for a while now, metals are losers. All right, metals are losers. Now, they can gain, which means what? Those are the nonmetals. And then I know that most of you are like, oh, I know what sharing is, but chemistry doesn't usually make sense. So it's not the metalloids. That would be the obvious answer. So a metal will lose, a nonmetal will gain, or they share electrons. Sharing happens when 2 nonmetals combine. So if you think about it, a nonmetal always has to gain electrons. So it can gain them by stealing from a metal, but if it's with another nonmetal, they have to share them. That's the only way they can work it out. All right, so anyway, moving on. They can do those 3 things to change their number of electrons so as to acquire the stable electron structure of a noble gas. How many valence electrons does a noble gas have? 8. And that is why this rule is called the octet rule. Every atom we draw, like dot-wise, so Na has 1, F has 7, 1, 2, 3, 4, 5, 6, 7. They all want 8 or 0, because really 0 means they have 8, like in the shell below them. So what sodium does is it gives fluorine its only dot. And now fluorine has 8. Sodium has 0, but really sodium has 8 as well because it chemically became like neon and has 8, just one level lower. Okay, this is the octet rule. This is why water is water. If you think about it, hydrogen has 1 electron. Oxygen is in family 6. So 1, 2, 3, 4, 5, 6. Here's another hydrogen with 1. The hydrogen gives it here, and that makes HO. But oxygen still needs 1 more, so then it goes here. So whenever oxygen and hydrogen combine, they form a H2O molecule. Water is a 2H to 1O ratio in order to satisfy the octet rule. Fair enough? Okay, let's call that good.